Hi everyone. We will talk about linear equations. What are these? These are ODEs of the following form. So coefficient, which is a function of x, times single derivative of the solution, and then coefficient times the solution equal to a forcing function. These are called linear equations. Okay. All right. Let's look at some cases. So if the forcing is zero, it's called homogeneous linear equation. If the forcing is not zero, it is called non-homogeneous. Okay. All right. And if we divide by a1x, and this is with a caveat, because we have to make sure it's not zero. For x such that we get, let me make some space. We get dy dx, p of x, y, and g of x, where p of x is the ratio of the coefficients, and g of x is the ratio of the forcing over a1x. And this is called and it's called the standard form. Okay. So when we ask you find the standard form, we just mean divide by the leading coefficient a1x. Okay. That's just because it will give us a quick method of solution. Okay. So now let's do some examples. First, we have an homogeneous one. So let me. So it was 1 over x dy dx minus 2y equal to 0. We will solve some of them in the next clips. Here's another applied example. Consider the RL circuit. So right over here, we have resistance, inductor, and then the voltage. So the equation that we will derive in a different clip is of the following form. So L R Y equal to a um, periodic voltage. Okay, and here I is the current. Okay, let's do one more, and then I will convert them to standard form. So another example is a non-homogeneous. So this is also non-homogeneous. This is like the forcing. So here's a non-homogeneous. Cosine x. Okay, so now let me convert them into standard form. So standard form, we simply divide. Um, so we so a1x here is 1 over x. So we divide by 1 over x. So we get this guy, and here we get x, right? Equal to 0. So that's the standard form. Let's see here. A1x is the constant L, the inductor. So we get dy dt plus r over L I equal to 1 over L sine 10t. Okay. And here we have dy dx minus 2 over x and x squared cosine of x. Okay, let's see. Okay, so I have time. I can do one non-example. So in general, nonlinear equations. So here's one Bernoulli equation. And it's of the following form. So dy dx plus a coefficient, but then on the right we have a power y to the n, where n is a 0 or 1, sorry, 2, 3, 4, and so on. Okay. So why do I mention this? So this equation is not linear because of the yn, but it can be turned into linear. So it's not linear, and it can be turned into linear via u of x y, where am I? Y to the n minus 1x. So if you do this substitution, let's say for example, just to keep it concrete, where am I? So suppose we have 1 over x, y, and x. So if this is the example, then u satisfies the following: du dx minus 1 over xu equal to minus x. Now this is linear, and that's pretty cool. So with substitution, so the lesson here is with clever substitutions, we can sometimes turn nonlinear into linear. Okay. So in the next